Hello everybody, welcome to the course VLSI Design Flow RTL to GDS. This is the tutorial for the 6th week. In this tutorial, we will be looking at logic optimization. Specifically, in this, the objective of this tutorial is to gain a hands-on experience on logic optimization using open source tool Yosys. And the requirement for this tutorial is that you should have Yosys installed on your system. So, the installation and how to run Yosys was described in tutorial 5. So, if you have not yet installed Yosys on your system, please install by taking help of tutorial 5. And in this tutorial, we will also need a few files. The first one is the design file top.v, then we need the script file opt.tcl and not_opt.tcl and technology library toy.lib. So, all these files are available on the NPTEL website as study material for week 6. So, you can download those files and then run the tutorial at your own at your end by using these files. So, in this tutorial, we will be looking at an optimization strategy which is known as resource sharing. So, we have discussed resource sharing in lecture 13. So, resource sharing is basically tries to save area in our design by using the same resource for multiple computation. So, let me recap what we had discussed about resource sharing in lecture 13. So, suppose there is an RTL construct in which there is a statement like if select is equal to 0, then z is assigned a multiplied by b, else z is assigned x multiplied by y. So, if there is an RTL construct like this, then a direct translation of this RTL construct will lead to a circuit something like this. So, we have two multipliers, one multiplier corresponding to a star b or a multiplied by b and the other multiplier for the operation x multiplied by y. And then using the select line, either the output of one of the multipliers is selected and produced at z, right. So, this is the direct implementation, but we can actually save the resource, the most costly resource in this circuit is the multiplier. So, multiplier typically occupies large area and therefore, we will want to use less number of multiplier in our circuit. So, what the tool can do is it can transform the original circuit of this to the circuit which is shown on the right hand side. So, in this case we are using only one multiplier and the multiplier gets input through the multiplexer and either A and B or x and y, those are supplied as input to the multiplier and finally z produces either A multiplied by B or x multiplied by y depending on the value of the select signal. Now, let us look into that or let us carry out experiment using open source tool Yosys to understand that how resource sharing is done by the tool and what is its impact on the circuit area. So, let us run the tool and see what happens. So, before running the tool, let us see that whether we have all the files that are required for carrying out these experiments. So, we have the script file and we have the design file and also the library. Okay. Now, let us first look into the design file top.v. So, I am using the editor GVim, you can use any other editor also. So, now if we look into this design in this Verilog code, we have a top module whose name is top and it has only one module, right. So, this Verilog file has only one module, and then within this always block we have the RTL construct that we talked about, right. So, we expect that the tool will actually optimize this or will implement this circuit optimally by using only one multiplier. So, now let us first run the script, that is not opt dot tickle, right. So, not opt dot tickle does not do the resource sharing optimization. So, let us first see that if we do not do optimization, what will happen, right. So, we now invoke Yosys by typing in Yosys, right. So, Yosys is already installed on my laptop, and that is why I can just invoke Yosys, and then we read the design, translate processes, that is our always block to netlist, and then do some cleanup to remove unused cells. So, we copy these lines of code and paste it in Yosys shell, right. So, we run these commands. So, now our design is loaded and no optimization is done, right. So, we can run the command show and see that what is how is our design looking like, right. So, when we run the command show, then this is displayed. So, we can see that there are two multipliers, one multiplier and the second multiplier, and the inputs are A, B and X, Y, and it is going to multiplexer, and then it is going to the D flip flop and to the output, right. So, this is unoptimized version of our design, right. So, we close this window and return to Yosys shell, right. So, Yosys throws out a quite a few warnings and some messages which we can safely ignore. These are related to the GUI that we open after running the command show. So, these are not important warnings or messages, and we can simply ignore them, right. Now, once we have got this design, we do mapping to internal cell library, then we do mapping of the flip flops to the cells in our library, and then map the rest of the combinational circuit elements to the cells in our library, and then do the cleanup, and then tell the tool that give us the statistics about the design. So, it will report the area. So, we copy these all commands and paste it in the Yosys shell and run it, right. So, the design was synthesized and finally, it reported the area, the chip area as 13,944. So, this is the chip area in library units, right. Now, we can actually get the Verilog netlist out of it by running this command. We copy this command and paste it in Yosys window. So, we get the final netlist as netlist underscore final underscore unopt.v, because we have not carried out the optimization, right. So, we exit now the Yosys shell, right, and we can see that whether our netlist was created, right. So, this netlist is created, and this netlist contains instances of the library cells. So, we can open this netlist and see what is this content. Okay. So, we can see that there are inverters, NAND gates and so on, right. There will be flip flops and other cells from the library, right. So, there are flip flops also and multiplexers, there are some multiplexers, and we also have flip flops DFF, R and Q. So, these are flip flops. So, the circuit got synthesized and the instances from the libraries were picked and put in the netlist. Now, the next thing is that now let us run the script which is doing the optimization, right. So, we open this file opt.tickle, right, and then again invoke the Yosys or tool, right, and first we do the same thing that we had done for an unoptimized thing, that script, that is load the design, right, and then convert the processes or synthesize the processes, and then ask it to show the netlist, right. So, the design currently contains 2 multipliers as earlier, right. Now, after this what we do is that we carry out some more commands, or we run some more commands in Yosys shell. So, these commands are opt and share manus aggressive. So, this command is basically sharing the resources. So, let us run these two commands. We copy these commands and paste it in the Yosys shell. So, now we expect that some optimization must be done. So, there are messages here. For example, it is saying analyzing resource sharing options for multipliers, right. And then it is saying that according to SAT solver, these pairs of cells can be shared. So, the tool actually inferred or detected opportunity of optimization and it transformed our design to a new design. So, what is this new design? Let us look at. So, we run the command show, then it will display the updated design. So, we can see that now we have only one multiplier is here, and there are multiplexers which is selecting either A to X or B to B and Y, right. So, this is the optimization that we have discussed and the tool has done it, right. Now, we do the same thing that we had done earlier, that is do the technology mapping and ask it to report the area and other statistics about the design. So, we copy this command and paste it in the Yosys shell, right. Now, the chip area is being reported as 7,546. So, remember that earlier it was around 13,900 or so, right. So, the chip area has now decreased, right. So, this is what we expect out of resource sharing, right. So, to get the netlist, we can run the command write verilog, right. We copied this and paste here, and now we expect that the tool must have generated this netlist underscore final underscore op.v. So, we do ls minus lrt to see the most recent file. So, the most recent file generated is this one, right. So, this is then optimized netlist in which there will be less number of gates than in an unoptimized version, right. So, we can also see that the size of this file is lesser, right. So, the optimized netlist has got lesser size, right, this one compared to unoptimized one, right. So, the number of gates in the optimized netlist is less, its size on the disk is also less, and the tool has done resource sharing. So, to summarize, in this tutorial what we have done is that we have looked into that how a synthesis tool, open source synthesis tool Yosys performs resource sharing, right. So, we carried out experiment to understand that how resource sharing is done by the tool, right. So, now this is just one of the examples of logic optimization. Now, you have got a library, you have got an open source tool, and you can write the Verilog code and carry out many more such experiments at your end, which will help you understand this logic synthesis tool and its optimization in more detail. So, that is the end. Thank you very much.